chapter chapter 9, electronics. I already uploaded the note in the group. You will check that. So here, in electronics, we deal with especially semiconductors. We deal with semiconductors. So what are these semiconductors? First subtopic, semiconductors. Semiconductors. So semiconductors are substance whose conductivity is less than a conductor and greater than an insulator. Semiconductors are substance whose conductivity is less than a conductor but greater than an insulator. So this semiconductor is in between conductor and insulator. First point. Second point, we can classify semiconductors into two, as intrinsic and extrinsic. So semiconductors are classified as first intrinsic semiconductors, and second extrinsic semiconductors. First, let us discuss about intrinsic semiconductors. So intrinsic semiconductors mean they are in the pure form. There is no any foreign body or any other materials added. Okay, they are pure. So intrinsic semiconductors, subtopic. Intrinsic semiconductors. So let's consider silicon semiconductor. So a silicon lattice. In a silicon lattice, we have a silicon atom bonded to 4 other silicon atoms. So the silicon is bonded to silicon. There is no any other impurities. There is only silicon in this lattice. So it is in the pure form. Then it is intrinsic semiconductor. So a bond is made up of 2 electrons. A bond is made up of sharing 2 electrons. So this is only a small sample. At room temperature, these bonds are strong, but still These electrons can absorb the heat energy from the surrounding and get excited to come out of this bond as free electrons. Now these free electrons can move, therefore they conduct electricity. Under this first point, intrinsic semiconductors are uh, elements in their pure form. In their pure form. At 0 Kelvin, at 0 Kelvin, at 0 Kelvin, the bonds are very strong. The bonds are very strong. So if the bonds are very strong, there won't be free electrons. All the electrons will be in the bond. Okay. At 0 Kelvin, the bonds are very strong. Therefore, no free electrons. No free electrons. Thus, they act as an insulator. So at low temperatures, the silicon will act as an insulator. At room temperature, valence electrons undergo thermal agitation. So what is this thermal agitation? That is absorbing the heat and getting excited. As I mentioned earlier, undergo thermal agitation and come out of their bonds and come out of their bonds as free electrons. Thus, their conductivity increases. Note number 1. Now let's say we have a silicon bond and the electron gets thermally excited and comes out to form free electron. Now it comes out to form free electron. So this electron, we call it as the free electron. And here we have a gap. We have a valency, right? A vacancy. So this vacancy we call as hole. So the hole is the absence of an electron. The absence absence of electron is hole. So let's say the charge of an electron, that will be minus 1.602 into 10 to the minus 19 coulombs, right? Then the charge of a hole, the charge of a hole. We know that when electron and hole combine, they neutralize each other. So if the electron is negative, then the hole will be positive with the same value. So plus 1.602 into 10 to the negative 19 coulombs. Now, these holes move in exchange for electrons. Let's say we had an electron here and a hole over here. So this electron can jump into this hole. So the electron moves forward, and the hole moves backward. So electron moves in this direction and the hole moves in the opposite direction, because this hole always moves in exchange for an electron. So the direction of motion, the direction of motion of holes of holes and electrons are are always in opposite directions. Are always in opposite directions. So, which one has more speed? Whose velocity is greater? The free electron or hole? Now let's say this free electron, this free electron can freely move in this lattice. Okay, in this silicon lattice, it can freely move. But the hole only can move when an electron moves in exchange for that place. So this can move freely, but this has to wait for an electron to exchange its places. Therefore, the free electron has a higher drift velocity when compared to that of a hole. The drift velocity, the drift velocity of electrons drift velocity of electrons is always greater than for holes, since the motion of holes takes place since the motion of holes takes place holes takes place always in exchange of bonds. Since the motion of holes takes place. Always takes in place in place of exchange with bonds. So every time a hole will exchange its place with another bond. Okay, it cannot freely move. It has to move from bond to bond. For example, let's say we had a silicon atom, silicon. Now, we have a gap here, a hole, and an electron. So when this electron fills this gap, then the hole moves in the opposite direction. So it is jumping from bond to bond. It is jumping from bond to bond. You're copying with me, right? So when we consider an intrinsic semiconductor, both electrons and holes, both of them conduct electricity. Okay, in semiconductors, in semiconductors, both electrons and holes, both electrons and holes conduct electricity. So I is equal IE plus IH. Okay. Are you copying with me? Have you noted up to the fifth note? Okay, the sixth one. Now, Saja and yeah, Saja is okay. Shaham, okay, right? So, if we consider an intrinsic semiconductor, in an intrinsic semiconductor, if one of the electron gets thermal thermally excited or thermally agitated, then it will form a free electron. When it forms a free electron, the number of hole formed is also equal. Okay, so in an intrinsic semiconductor, in intrinsic semiconductor, intrinsic semiconductor, Ne, number of electron, is equal to the number of holes. Okay, number of electrons is equal to the number of holes. Number of electrons is equal to the number of holes. Number of holes. So, what if we increase the temperature? If we increase the temperature, obviously, number of holes and number of uh, thermally excited electrons is going to increase. Then, if E and H increase, number of E and H increase, obviously, it is going to increase the current flow. Okay, so when temperature is increased, when temperature is increased, when temperature is increased, when temperature is increased, Ne and NH also increases. Also increases. Therefore, current increases. When it comes to current in electricity, in conductors, we discussed that when temperature is increased, resistance increase, therefore current decrease. But here it is the opposite. When temperature increase, resistive decrease and current increase. Okay. Seventh note. I hope you can remember this equation. I is equal to NEVDA. I never forget this equation. So here, from this equation, it is clear that if N or VD increases, I increase. In intrinsic semiconductor, Ne is equal to NH, but velocity of electron, drift velocity of electron is greater than the drift velocity of hole. Therefore, if we compare IE and IH, therefore IE is greater than IH. And we also can consider that the current in this intrinsic semiconductor is almost equal to IE, since IH is negligible. Okay, IH current is negligible when compared to IE. Therefore, we can straight away consider that the current due to the flow of electron is the current. Now, uh, as we discuss, we want to increase the conductivity of these semiconductors. For that, increasing the temperature is one method, but it is not the best method. We are trying to get another method. Just think, increasing the temperature, you might melt the uh, device, right? These electronic devices are very small devices. So when you increase the temperature, it might melt it. So we have some other ways. That is by doping, by adding some impurities. Those types of semiconductors, we call them as extrinsic semiconductors. The next subtopic, sorry, next subtopic, extrinsic semiconductors. Extrinsic semiconductors. So, as I mentioned earlier, these extrinsic semiconductors are formed by adding some impurities, adding some foreign objects, foreign atoms. So here we can use group 3 or group 5 element. A small amount of group 3 or group 5. A small amount of group 3 or group 5 element is added to intrinsic semiconductor. Intrinsic semiconductor. So this process we call it as doping. This process is called doping, and this which increases the electrical conductivity. Which increases the electrical conductivity. These extrinsic semiconductors can be further divided. Extrinsic semiconductors are classified uh, classified uh, classified as first N-type and second N-type semiconductor and second P-type semiconductor. Another we have first type N-type semiconductor. N-type semiconductor. N-type, that means negative type. Negative type semiconductor. Okay, first point. N-type means negative type semiconductor. Give me 2 minutes. So N-type semiconductor. Here we dope with a group 5 element. For example, phosphorus. If we consider phosphorus has 5 valence electron. Phosphorus has 5 valence electron. So 4 of the electron will form bond, and the one extra electron, it will act as a free electron. To increase the conductivity, we need free electrons. By doping it with a group 5 element, we are creating a free electron without any thermal agitation. So this will increase the electrical conductivity of this silicon lattice, or this semiconductor. A group 5 element is doped or group 5 element are doped at the ratio of one phosphorus is to 1 million silicon atoms. So look, for very large amount, we are only adding a phosphorus atom. By adding this small amount, we can increase the conductivity by a very large amount. So adding a very small amount of impurity will increase the conductivity by a huge amount. So here, group 5 elements have 5 valence electrons. In which 4 electrons form bonds with silicon, and the fifth electron and the fifth electron acts as an free electron. So this group 5 element is contributing an additional free electron. Therefore, we call this group 5 element as donor atoms. Okay? Because group 5 elements provide additional electrons. They are called donor atoms.